Let's look at standardizing normally distributed random variables. The standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. The standard normal distribution comes up frequently in probability calculations and statistical inference, and we'll soon see that we can convert a random variable having a normal distribution with any mean and standard deviation into a random variable that has the standard normal distribution. This will help with some probability calculations. We deal with the standard normal distribution very often in statistics. Suppose x is a normally distributed random variable with mean mu and standard deviation sigma. We can write this as x is distributed normally with a mean of mu and a variance of sigma squared. This isn't universal notation, and some sources write the standard deviation as this second term, so we have to be a little bit careful. But my notation with the second term representing the variance is pretty common. Now we are going to standardize this. We're going to turn this into a random variable that has the standard normal distribution by using a basic linear transformation. The random variable x has a mean of mu, so if we were to subtract mu from x, then this quantity is going to have a mean of 0. And if we divide by the standard deviation sigma, then we are forcing this quantity to have a standard deviation of 1. This is a linear transformation on the random variable x, and the transformed variable has a mean of 0 and a standard deviation of 1. I'm going to call this quantity z. And here, z is a random variable that has the standard normal distribution. We could write this as z is distributed normally with a mean of 0 and a variance of 1. Note that by subtracting the mean and dividing by the standard deviation, we are forcing the random variable to have a mean of 0 and a standard deviation of 1. This doesn't change the shape of the distribution. Here z is only normal because x is normal. But if x had a different distribution, then z would not be normally distributed. Now let's take a look at how we might use this in probability calculations. Suppose the height of adult American females is approximately normally distributed with a mean of 162.2 centimeters and a standard deviation of 6.8 centimeters. This is close to reality as estimated by National Health Statistics. And that distribution looks like this. Here the mean of 162.2 is right in the middle of the distribution. The normal distribution is a symmetric distribution, so the mean and the median are equal. Suppose we want to know the probability a randomly selected American female is taller than 170.5 centimeters. If we let the random variable x represent the height of a randomly selected female, then we are interested in finding the probability that the random variable x takes on a value that's bigger than 170.5. And that's simply the area to the right of 170.5 under the distribution of heights, which is this area right here. But it can help us find this area if we first standardize. Here we want the probability that the random variable x takes on a value bigger than 170.5, and I'm going to subtract the mean and divide by the standard deviation on both sides, and say that this is equal to the probability that the random variable x minus mu over sigma takes on a value that's bigger than 170.5 minus mu over sigma. I'm doing the same thing on both sides there, so I haven't really changed anything. Why did I do this? You might recognize this quantity on the left as z. We've standardized our random variable, and so this quantity here has the standard normal distribution. And so this is going to be equal to the probability that the random variable z that has the standard normal distribution is greater than 170.5. I'm now going to put in the value of mu and sigma here, and so I'm going to subtract the value of mu of 162.2 and divide by the value of sigma, which is 6.8. And this works out to the probability that the random variable z takes on a value that's bigger than 1.22. And here's the standard normal distribution. And the probability that z takes on a value that is greater than 1.22 is the area to the right of 1.22 under this curve, this area. If we go to software or a standard normal table, which we've looked at previously, we can find that this area is approximately 0.111. So this area is 0.111, which means that the area to the right of 170.5 under the original distribution is 0.111, and the probability that a randomly selected adult American female is taller than 170.5 centimeters is approximately 0.111. The Z value tells us how many standard deviations a value is above or below its mean. So this Z value of 1.22 means that 170.5 is 1.22 standard deviations above the mean of 162.2. So we just figured out the probability that a normally distributed random variable falls more than 1.22 standard deviations above its mean. What is the probability a randomly selected adult American female has a height between 150.5 and 170.5 centimeters? Here we want to find the probability that the random variable x takes on a value between 150.5 and 170.5 centimeters. And if we draw out our original distribution here with 162.2 in the middle, 170.5 is over here somewhere, and 150.5 is over there somewhere. And this probability is equal to the area between those 2 points. Now we're going to standardize by subtracting the mean and dividing by the standard deviation. So this is going to be equal to the probability that the random variable z takes on a value that is greater than 150.5 minus the mean of 162.2 divided by the standard deviation of 6.8, and is less than 170.5 minus the mean of 162.2 divided by the standard deviation of 6.8. This works out to the probability that the random variable z takes on a value between minus 1.72 and 1.22. And that is simply the area between those two values under the standard normal curve. So if I were to draw out a standard normal curve and put 1.22 over here somewhere and minus 1.72 over here somewhere, we are looking for this area. I'm going to let you verify for yourself using software or a standard normal table that this area is, to 3 decimal places, 0.846, which implies that this area under the original distribution is also 0.846, and the probability that a randomly selected adult American female has a height between 150.5 and 170.5 centimeters is approximately 0.846. Now let's look at a different type of question. What is the 10th percentile of the height of adult American females? The 10th percentile is the value of the variable that has an area to the left of 0.10. So over here somewhere is the value that has an area to the left of 10% or 0.10, and this value there is the 10th percentile. We can find that value rather easily by first finding the 10th percentile of the standard normal distribution, then converting back to this distribution. And here's a rough sketch of the standard normal distribution, with 0 in the middle, and over here somewhere is the value that has an area to the left of 0.1, and this would be the 10th percentile of the standard normal distribution. And if we go to software or a standard normal table, we can find that this value is approximately minus 1.28. The area to the left of minus 1.28 under a standard normal curve is approximately 0.10. And so minus 1.28 is approximately the 10th percentile of the standard normal distribution. And since we know that z is equal to x minus mu over sigma, if we rework this, we can see that x is equal to mu plus sigma z. And so the 10th percentile of the distribution of heights is going to be equal to 162.2, the mean, plus the standard deviation of 6.8 times the 10th percentile of the standard normal distribution, which was minus 1.28. And this works out approximately to 153.5 centimeters. And so this value on this curve is approximately 153.5 centimeters. And the 10th percentile of the distribution of heights of adult American females is approximately 153.5 centimeters. We'll find that standardizing normally distributed random variables comes up frequently in theory and practice, and so we'll often have to use these techniques.